A part of my thesis today that was a joint work with Roxana and Peter. So we will talk about game theory today. So for the introduction, this talk was aimed to last around 15 minutes, so I have time to explore more. So I think it's been the 5th day, so everyone is maybe tired. I actually thank you to be here this morning. So I will try not to overflow you. So I guess so far at this stage of the workshop, you know that we have a context of energy transition, and this requires an increasing share of renewable energy and closure of coal-fired power plants. And the recent crisis we experienced those last year, for example, the Ukraine crisis, enlightened that there is a risk in the meantime, while doing this transition, to rely on gas power plants. And this can be some trouble for the electricity supply. But at the meantime, if you want to model the investment dynamics in power systems of power plants, it's challenging. Usually, you will have a RTE's approach, for example, where you will have some greenfield approach, meaningly you will imagine you have nothing and you will build all the power plants in one shot. In reality, that's not exactly what's happening because there is a market and the states are waiting for the power plants to be built based on the market revenues. So that's something that is a little subtle. So then we have a market framework that is dynamic because you have repeated interaction and you have many players. We are talking about hundreds and sometimes thousands of players on that market. And this market involves uncertainty on the production because today when you are building the wind turbine, you are not sure about the production in 5 years, for example. You have some uncertainties on the cost because maybe the gas price will rise in the long term. Maybe the technology investment cost will decrease if you wait enough. And on top of that, we have environmental policies. We have a market, so it's supposed to be self-sufficient, but on top of that, because we have some governments trying to push for more renewable, they are adding some additional environmental policies on this market, like a carbon tax, some renewable subsidies, sometimes they even had carbon emission constraints, even outside of the market. So this whole picture is a bit complicated. So to model it's challenging. So today in this talk, we are talking about how to model entry and exit dynamics in the electricity market, considering that all of the agents are anticipating other agents' action because it's a market. We are taking into account uncertainty on the production, on some investment costs, and environmental policies. So this paper today is already published. It was published in Quantitative Energy Finance, so with Roxana and Peter. But today I'm presenting an extended version that was done in my PhD thesis. So we went a bit further. So in this paper, we present a long-term model for the dynamics of the electricity industry to describe this energy transition. We introduce the notion of strategic interaction, meaning that all of the agents will try to anticipate what other agents will do. We account for agents' heterogeneity, meaning that not all the power plants will behave the same, even with the same technology. We added a construction lifetime and endogenous fuel prices. So what I mean by that is that we added an external fuel market that will drive the fuel prices. We prove the existence of an equilibrium with the uniqueness of electricity and fuel prices. So we will prove that in this model we can find the equilibrium. And even if we have several equilibrium, we have the same electricity and fuel price for all the equilibrium. So that's not a problem. An extension in the PhD thesis was to include a mean-field control central planner. So it means that we introduce a counterpart of the model when we have a market coordinator that will control the whole market and control the entry and exit on the market to try to optimize the general welfare of the economy, so including the consumers. And finally, we analyze the dynamic of entry and exit in a case study based on Germany with environmental policies. So we will try to understand how environmental policies change the entry and exit dynamics.
Excuse me. So since you have really irreversibility, or you in one long lifetime of your power plants, and you have uncertainty, do you have any interpretation in terms of option values or real options?
No, we did not consider real options. Okay, so a bit of literature here. I promise it's the only slide about it. So there is a classical classification of electricity market-related models that it's a bit old now, but it's still the one that is used. And with time, it became more porous. First, you have the market equilibrium models. If you had some economics class, that's the one you probably dealt with. So you have Cournot equilibrium, classical market equilibrium. The main strength of this model is to have really a tractable equilibrium concept. You have closed form solution, closed form equations. You really know what's going on in the model. But then, to have that kind of equilibrium, you have to make usually a lot of simplifying assumptions. Usually, it's static models. You have some dynamic Cournot model existing, but they are more complicated and not frequent. You usually assume homogeneity of the agents, so you will solve the model by symmetry, by saying that all the agents behave the same, and you can have a symmetrical equilibrium. So that's one of the main drawbacks of that kind of model. Then you have optimization models. I think EOL, for example, that was presented before, is that class of model. It's engineering models that are representing large power systems. Their main strength is because they are really powerful and large model, able to represent a lot of stuff, a lot of physical constraints, high time granularity. You can deal hour by hour. But then the problem is that in that kind of model, you usually have a central planning approach where you optimize everything. But you don't have that idea of agents interacting with each other with an equilibrium concept. But it's not made for this purpose, so that's not a critique of that kind of model. And then the last comer was the simulation model. For example, you have agent-based model. The purpose of that kind of model is to simulate the behavior of large power systems. So in that kind of model, you actually take into account agents' interactions over time, usually with a behavior rule. But then the problem is that it's a bit difficult to compute and to interpret because, again, even if you have some agents interacting, you still don't have that closed form equilibrium solution really allowing you to say this is an equilibrium here. So that's one of the problems. So here I'm presenting mean field. So mean field theory, and in this case mean field game, is a market equilibrium model. But that allows for many relaxing assumptions, allowing us to be close to simulation models. So it's a game concept that works well with many players. That's the case with electricity. But we still get a tractable solution, and we can do relaxing assumptions like agents heterogeneity. So in this model especially, we will allow for non-symmetrical equilibrium. And this framework is particularly suitable if you want to introduce uncertainty. And we were able, with this model, to add endogenous fuel price. So now I will present the model. So in this model, each producer is divided into categories. We have three main categories. The first one being conventional power plants. Conventional meaning fossil fuel, or it can be nuclear, but like really classical thermal power plants. We have renewable power plants, and we have baseload power plants, but I will talk about this one lastly. For conventional power plants, and in general for each of the technologies, you can still subdivide this category into technologies. So for example, for conventional, you can definitely have coal-fired power plants, several kinds of gas technologies, some nuclear, and their main similarity is the cost function form. So the conventional power plants will choose to produce between 0 and 100% of capacity each hour of the model. And the marginal cost of producing this capacity will be composed of some operating cost, it's like really engineering cost, some fuel cost, so the fuel you are spending to produce the electricity. Here I would like to drive your attention on the fact that you can have several technologies using the same fuel. It's not each technology has one fuel. You can really have, for example, two kinds of gas power plants, both using gas as a fuel, but having different cost components. Then you have the carbon cost, so it's related to the fuel that is used by the power plant and the carbon price, and you have some conversion factor, because if you take coal, for example, using coal is twice as polluting as gas. And if I didn't use nuclear in the case study, but if I use nuclear, it will be close to zero. And finally, you have a random cost component that is individual to each producer. So this component is really here to capture the unobserved cost due to each of the producers. Because in the theory, you would be supposed to have each of the gas power plant to bid the same cost on the market, for example. But in practice, it's not the case. You have some disparities that cannot be really explained. So here, this component will capture all this disparity. And this will allow us also to introduce some heterogeneity, because maybe if you're in France, for example, EDF will not manage a gas power plant the same way Total would, even with the same technologies. So this can explain a lot of stuff. Then you have the renewable power plants type. Again, you can have several sub-technologies. And they are only characterized by a random production factor, S, that follows a Jacobi process here. And the renewable power plants bid their entire possible production on the market. So an implicit assumption here is that if we have too much renewable power on the market, then the regulator will just cut it for free. That's a simplifying assumption. And finally, just to capture all the power plants we did not properly modeled but are still on the market operating, we constructed an aggregated supply function representing the baseload power plants function. That's really for calibration matters. It's where you will put the hydro power plant, for example. And they are unaffected by the market dynamics. Namely, they are not entering and leaving the market. It's us that set it exogenously. So now on the market, how does it happen? So we have the electricity price that will be derived by matching an exogenous electricity demand and the aggregated supply of electricity considering the agent's bid on the market. So on this market, the conventional producers will choose a fraction of their power plant to put on the market, and they will choose this factor to maximize their revenues. And for renewable, it's simpler. They just offer full production. So if they can produce at 30% of capacity, they will offer 30% of capacity on the market. In case of market failure, so if we have an excess of demand compared to the supply, then the electricity price does not go to infinite, but is capped at P star. Again, it's a standard and realistic assumption, because for European market, that's the case. And then you also have the fuel market, where each fuel type has an exogenous supply function, so an exogenous gas supply, for example. And the fuel price will be determined by matching this supply function and the total fuel required to bid the electricity production. So now comes that strategic interaction. I said it's a dynamic problem, so the market will be repeated, and for the producers, the strategy, so the aim is to choose an optimal entry time and exit time, so TO1 and TO2 here. And they will choose this time such as they maximize the expected revenues on the market conditional on the cost of entry and the recovery cost if they leave the market. So that's the case for producers not on the market, and for producers already in the market, because we can initialize this problem with some power plants already on the market, they are just trying to choose the optimal exit time. So why do we have to choose that exit time? For coal power plants already on the market, for example, there is an incentive to leave earlier because, for example, they don't want to face the carbon tax that is growing with time. They also want to recover some cost, and if they wait longer, the dismantlement will be more expensive. But at the same time, if they wait more on the market, they will still gain some revenues for the market. So there is really this arbitrage effect. While for the potential producers, especially the renewable, there is an arbitrage between earning a lot on the market by entering first. But if they wait more, there is a decreasing cost of investing in renewable. So if they wait, it will be cheaper to actually enter the market. That's why we have those dynamics. And on top of this problem, we had fixed costs, like annual year fixed cost, some construction time, because even when you take the decision, it can take several years to build a power plant. We also have the possibility to include the plant lifetime. I did not in the case study, but it's in the model. And so I talked already about the dynamic investment cost. And finally, that's a small novelty. We built the central planner. So the central planner will solve the aggregate problem where it tries to maximize the welfare of all the economy, namely the revenues of all the producers, minimizing the price paid by the consumers, maximizing the fuel market revenues. So basically maximizing everyone's revenues at the same time. And we actually showed in the paper that it's equivalent to the game version. So I'm not talking more about it before the end of the talk, but just so you know, the problem were proven to be equivalent. So now, game theory aspect. So as I said, the strategy of all the players are to choose optimal entry and exit time. So the strategy will be a set of entry and exit time tau without incentive to deviate considering other player entry and exit time. And if you did a bit of game theory, you will know that if you have many players, it becomes really complex to solve because you will have one agent thinking about all the strategies of agent 1 to 100. So that's a lot. If you play chess, you will probably get a headache at some point. So here, that's when we introduce mean field. So the trick with mean field is that we will replace the whole agents by an infinite population of agents represented by a measure. So we will consider the case when we don't have 1,000 players, but an infinite number of players. And then, because we have an infinite distribution of players with some random variables I introduced earlier, you can consider a whole distribution of players. And in this setup, then, a mean field Nash equilibrium will arise when a representative agent of a class, so the class was conventional and technology, will have no incentive to change the entry and exit time considering the general distribution of all the other players. So we are neglecting the pure individual effect but focusing on the aggregated mass of the player here. And here it's nice because if you consider a measure of the player, then you can actually rewrite the problem as a linear function of the occupation measure. So then it becomes a linear problem, so you can use linear programming approach. So far it's okay. I can show the math later if you want, but I just don't want to lose you. But just think about, it's easier to think about the aggregated distribution of the agents rather than each of the agents individually. That's way simpler in math. We just needed to add linear constraints because we had some random variables, so we just need to ensure the problem and the solution will match the physical behind the random variables. And then our Nash equilibrium will be a sequence of entry and exit measures by class of technologies and price function such that the measure will maximize the conventional maximization revenues program, the renewable producer program, and the price function will be, the price will be derived by matching supply and demand. Mm-hmm.
Can I ask you a live question?
Sure.
If we try to make the connection between such a model and what happens in the real life,
mm-hmm.
so does it mean that any producer has the information about what happens with all the others?
Not exactly all. He doesn't know exactly the position of the player, but he has an idea of the distribution because he, for example, he doesn't know the cost of each of the competitor, but he knows the distribution of the cost. That's that answers.
And another question: is there an associated assumption of atomistic agent? Does it change something if you remove one of them?
No. No, if you remove one agent, because we assume that there is some infinite population, then removing one agent does not matter. That's really the strength of mean field is that you still have that strategic interaction, so it's not pure price-taking agents, but you consider that if you remove one agent or one agent alone does not have the power to deviate the market. But if enough players move, they can deviate the market. That's the idea. So that's really a way to visualize mean field game is fish school. If you remove, you have the fish that are usually moving as a school, so there is some idea of strategic interaction because they don't move just randomly. If you remove one fish from the school, it will not deviate the school, but if you remove enough fish, most of the fish will follow. That's exactly the same idea. So we'll go to we can stop with the theory and let's go with the illustration now, then you will understand exactly what does this model do in practice.
Alicia, because you say before that there was an equivalence between a kind of first best of entry and exit and the mean field solution. So
oh, that's the central planner.
Yeah, okay. I mean, because you would see, so because you would have the same result if agents would be a price taker also?
Not exactly, because here the central planner is not the central planner here. That's because I did not go into detail. The central planner, contrary to a big optimization model, will not choose the entry and exit and the production behavior, the bid behavior on the market. It will just control entry and exit, but then the players will still act on their own on the market. That's the main difference. So there is still a small difference.
But I guess it's also because you do not have other market imperfections.
No. No, it lacks some market imperfection at this stage. Like information, I think incomplete information could be an interesting idea in the long term. At this stage, it's still a relatively perfect market.
So if you say that, you feel okay, there is no need for administrative closing of coal power plants.
That's a good question, but we can add that on the model. That's why I didn't have the time during my thesis, so it will probably be another paper. But the idea of having a central planner is actually to represent what if we had exogenous shutdown. So we force the actors to stop at some point. So that's the idea behind still preparing a central planner aspect. But that's exactly for that kind of case. Okay, so I will show you a small toy example on the Germany data. So we will simulate 25 years of Germany power system with 24 representative hours per year. So I did not model the full set of hours. And we distinguished between peak and off-peak hours, and we assumed a 2.3% annual growth of demand. That's based on the International Energy Agency provision. We only considered coal, gas, and wind technologies for entry and exit. All the other power plants were added to the baseload supply curve. And we specified a 3% reduction in renewable investment cost to represent a learning effect. That's International Renewable Energy Agency projection. So we considered a carbon tax linearly going from 20 euros today to 200 euros in 2045. Again, that's regular provision. And we considered subsidies starting in 2019 for renewable production that will decrease linearly decrease to reach 0 in 2045, because it's common knowledge of the policy that the government wants the subsidy to end someday and does not want to keep it going forever. So I will simulate entry and exit with these parameters. So first, I have a benchmark scenario. So what happens if I have no environmental policies? So in this model, what happens? First, you have a small decrease in coal power plants. That's due to the calibration of the model that will specify the model computed that the current number of coal power plants in Germany is not optimal and decrease it at the beginning of the simulation. So I was asked about this before. I think it's because in reality, you don't close the power plants immediately. First, because there are some technical constraints to do that we did not include it in this case study for simplicity. And also because in reality, you don't shut power plants just by snapping your finger, because there are some social and economic consequences to do that. You will have some people that will become unemployed, you just don't shut the power plants like that. So that's one of the reasons we have this adjustment. Then, in the long run, you have some gas power plants entering the market to answer the growing demand. And you have some renewable power plants entering in the long term when the costs decrease enough that it becomes profitable to enter the market, so renewables start to enter the market. But still, you can see that most of the supply is done by conventional power plants, so gas and coal. Now, if I add a carbon tax, what happens? With the carbon tax, you can see that the coal power plants are pushed out of the market even before 2030. So the carbon tax is effective to defer the coal power plants to stay on the market. The gas power plants still enter in the short term, but it stagnates in the long term. And you have a massive renewable entry to meet the growing demand. So the carbon tax, from a transition point of view, seems to be effective. But if we check closely, we can see that in the long term, at some point, the renewable production is not sufficient to meet the demand, and the gas power plant starts to produce more. So it's very likely that if I simulated not 25 years, but maybe 40 years, that at some point, the gas power plant will start to rise again. So why? I was going to answer that question, but that's a good question. That's one of the limits of this model, is that we don't have backup technologies or batteries. So at some point, the renewable energy is not able to meet the demand in some critical points because there is no wind, for example, and you don't have the backup technologies to counter this effect. So this model is not really well suited, I think, for 2050, for example. The purpose of this model is really not to represent the grid. Okay? It's really to represent dynamics of entry and exit. The storage option is currently developed by another PhD student of Peter working on this aspect. But that's why. So don't worry too much about that.
And, Alicia, excuse me, what is this increase of baseload plants?
That's because we do not change the baseload capacity. It's like the remaining nuclear power plants in Germany, the solar panel. So that's also one of the limits. We did not include solar in this simulation. So why we did not include solar? It's because of the random process. It's really hard to model a random process for solar. Because with a wind, you have like a continuous wind flow. It just doesn't go wind, no wind, wind, no wind. But that's the case with solar. So it's challenging, again. It's still challenging to model. Sorry?
Is there any particular reason you use Germany data instead of France? Maybe you use France data instead of using the maybe the nuclear energy.
That's a nice question. So why not using France? I think I get this question pretty often, actually. First, because France is not a reproducible example, in my opinion. Because due to the predominance of the nuclear power plants in France, it's not really, let's say, phasing out of the nuclear is a specific question that is highly political, and it's a really French debate. So I don't think it will make sense to model France, because then the model will not be suitable for Poland, for example. And in France, due to that, the production mix is already decarbonized, so the transition effect is different from Germany when you really have coal power plants that you want to phase out from. That's why. So back to the carbon tax. So in the long term, there is some problem, but this arises also from some model limits. But then you also have the electricity price that dramatically increase. Why? It's because when you have a strong carbon tax, it's passed through the cost function of the conventional power plants staying on the market, and they pass this cost through their electricity bid. So it's passed through the market price, and you have the strong electricity price. So that's one of the concerns with carbon tax in general. Then, if you consider a renewable subsidy, then you will have some renewable power plants entering quicker the market, but as long as the subsidy slows down, the penetration stopped, and the coal power plants are not really pushed out of the market. So it's not the most effective tool if you want to push coal out of the market, but the consequences of on electricity price are modest, so there is an arbitrage here. So I just have time to make a small discussion. So first, the gas power plants remain competitive because actually gas power plants are quite cheap compared to coal power plants, unless you consider surge in gas price. We didn't hear, but that's another thing we can consider in the long term. Lower emission compared to coal power plants and predictable production. And because we don't have those backup and storage technology, it's normal that in the long term gas is happen to play a role, but we can think about from maybe 2035 it could be replaced by storage, but still I think it's still necessary to enlighten that in the short to medium term, waiting for this technology, gas production can increase. This result was present before the Ukraine crisis, so that's something that could change. So if you don't consider environmental policies and you don't consider gas price surge, then it's likely that the demand will be met by gas power plants. So I talked already about the arbitrage between a carbon tax that is effective but rise the electricity price and renewable subsidies that are effective in the short term, not in the long run. And, oh no, I missed the discussion. So I talked about it a bit already, but we introduced the central planner in order to, in the long term, introduce more environmental policies, like having a carbon emission societal constraint, having exogenous coal power plant phase out. So that's really some future work. And maybe I hope I will present that in the long term. So thank you.